Hello, class. This is Mr. Hart. And in this podcast, we want to talk about general gravitation, which is the next part of our unit. And we've talked about gravity a lot in this class when we did the free fall equation. But that's specifically when we're talking about someone on the Earth, an object on the Earth, right? We were focusing on 9.8 meters per second squared, which is on the Earth. But now we want to look at the gravitational pull between any object, the Earth and the sun and the moon, the Earth and Jupiter, whatever it is, right? We want to look at how gravity affects any object in the universe, okay? And so we call this idea general gravitation, okay? And we can define it this way. It's the idea that all objects have a gravitational pull towards all other objects, okay? No matter how small, they all have a very, very, very small gravitational pull, okay? So for example, right now, I have a gravitational pull on the computer. The computer has a gravitational pull on me. I have a gravitational pull on the desk. The desk has a gravitational pull on the computer. I have a gravitational pull on you watching this, even though it's very, very small, right? So any object has a very small gravitational pull on every other object, okay? And so it is, again, very small, so we don't feel it, we don't realize it, right? So if we think about it, it's between any two objects, so why can't I just, use the force and reach out my hand and the remote will just fly to me, because of that gravitational pull? Well, again, it's because everything is so small, okay? And because everything is so small, every gravitational pull is so small, we really don't see the effects of it, okay? We have air resistance, we have, the gravitational pull of the Earth that holds us down. So these very, very, very small forces between all the other objects, okay, they really don't matter because it is such a small amount, okay? And so we're going to see, we'll look at it in a second, but we'll see that this gravitational pull needs to be described in scientific notation because it is so small, okay? And so if we're trying to describe the gravitational pull between any two objects, we're going to need a couple of things. First of all, we're going to need the mass of both these objects, okay, so like that hand and the remote, okay, we're going to need the distance between the two objects, okay. If they're very close, it's going to be a stronger pull. If they're very far away, it's going to be a weaker pull, okay. And the last thing is we're going to need to know how strong the gravitational force is in general, okay. So when we combine all those things together, this is the equation we end up with, okay. So let's go ahead and label this. So F sub g, which is how I notate the gravitational force. So gravitational force between any two objects, okay, is equal to this big G, which we'll talk about in a second, times mass 1 times mass 2 over r squared, okay? So the mass of the first object, the mass of the second object, and then the radius or the distance between the two objects, okay? So it's a pretty simple formula. We just find the mass of both objects, times them together, divide it by the distance between them squared, and then we times it by this big G, which tells us how strong gravity is, okay? So this big G has a special name, okay? It's called the universal gravitational constant, okay? So universal gravity or gravitational constant, okay? And again, it's just going to describe how strong the pull is between every object, okay? So for example, let's say I'm trying to find the gravitational force between me and the computer, okay? I'd take the mass of both me and the computer and divide it by the distance between us, and then times it by g to find out how much force there is, okay? So I weigh quite a bit, all right? Let's say 80 kilograms. And the computer weighs, let's say, 5 kilograms. So 80 times 5 would be, 400. We're not very far apart, so you'd expect this to be kind of a large number, a large force. But again, it's all going to depend on this universal gravitational constant. Okay. So make sure you got this written down, but let's look at what this big G is actually equal to. Okay. So when you look at it, you figure it all out, you find out that G is equal to 6.67 times 10 to the negative 11th, okay? That's really, really, really small, okay? That's 100th of a billionth, okay? So ridiculously small. So why is the gravitational pull on the Earth so big? It's, well, because the Earth is so big, right? The Earth is 10 to the 24 kilograms, okay? If the Earth wasn't this big, we wouldn't expect as much gravitational force. But that's why we are so used to feeling gravity, because the Earth is so big, okay? If we were just kind of out of space and we saw objects floating around, we wouldn't feel gravity that much because we didn't have that large gravitational pull, okay? So again, the reason we see gravity on Earth is because the Earth is so big, but usually gravity is a very, very weak force, okay? And don't worry about these units over here too much. They're just to help us cancel out everything when we put it into the equation. Okay, but this is the number to remember. 6.67 times 10 to the negative 11th. That is always what this big G is. Okay? All right, and so, in fact, when when Newton first wrote down this equation, okay, he didn't actually know what big G was. He just knew that there was this relationship between the masses and the distance, but he couldn't figure out what this, universal gravitational constant was. Okay, it actually had to be discovered by a man by the name of Henry Cavendish. Okay, so Henry Cavendish is accredited to having the discovering the universal gravitational constant. Okay, and what he did is, it was pretty much a crazy setup. He was kind of a quirky guy. He had a lot of strange habits, but this setup shows how meticulous he was. Okay, what he did is he hung two masses on a string like this. Had a bar across and had two masses on each side of the bar, and then he had them being attracted to two other masses. Okay, which is what you kind of would do if you were trying to think about how to get the gravitational constant. But the thing is that gravitational pull is so small that things like air friction and other things could get in the way. So what he did is he put it inside of a shed in his backyard, basically. He drilled a hole into the shed, and then he looked through like a telescope into the hole from the other side of the yard, basically, so that he wasn't interfering with this experiment. And then he looked at this tiny little mirror, and based on where he was looking at in that tiny little mirror, he could determine how much this had moved. He did this I think it was for 5 years, just day in and day out, okay? Just trying to determine how much this little mirror was moving, okay? And after all that meticulous work, he finally found it, and he was right within 5 decimal places. It's nuts. It's crazy that was so accurate with such a, primitive experiment for back then, but he was just very meticulous and made sure everything was aligned, and he put it in the shed so that it wouldn't be interfering with a lot of things, and it's crazy that it was that accurate, okay? But he is accredited to finally finding out how big G is, how much this gravitational pull is, okay? But like I said, he's kind of a quirky guy. He used to hold on to wires because they didn't really have voltmeters back there or amp meters back then. So he was studying electricity, and he'd hold on to wires, and based on how much they were hurting him, he could determine how much amp was going through it, how many amps were going through it. So he made his own amp meter out of himself by determining how much pain he was feeling. Okay, so based on how much shock he was getting, he could determine how much amps he was getting, basically. So again, kind of a very crazy guy. I recommend looking up some of his stuff because he had some interesting habits, but was able to discover this universal gravitational constant, which was amazing. Okay, but all right, let's go ahead and look at some example problems of how we actually are going to calculate this force between two objects. Okay, so let's do this problem. So we have an object with a mass of 1,000 kilograms and an object with a mass of 5,000 kilograms, and they're 2 meters apart. Okay, what is the gravitational force between them? Okay, so first of all, we need to do some identifying. We know that mass 1 has a mass of 1,000 kilograms. Okay, we know that mass 2 is 5,000 kilograms, and we know that the distance between them is 2 meters. Okay, so we're going to plug that into that big equation. Fg, force of gravity, is equal to G times m1 times m2 over r squared. Okay, so what I recommend to students as they're doing these problems is do this part first. Don't worry about G yet. Do the variables first before you try to plug in big G, because otherwise you try and times it and it kind of throws everything off if you're not careful with your calculator and that type of thing. Okay, So let's just leave G as it is for a second. So we get G times 5,000, or sorry, it should be 1,000, times 1,000, okay, over R squared, which is 2 squared, okay? All right, so we times that out. I'll put that over here. So 5,000 times 1,000 over 2 squared, and you simplify that. Let's put it on our calculators really quick. So we have 5,000 times 1,000 divided by 2 squared, or 4 basically. And we get that it is G times 1,250,000. Okay. All right, so that's what we got. So now this is where I tell students to plug in G. Okay, once they kind of simplify, now let's plug in G. So we're going to get G is, again, 6.67 times 10 to the negative 11th. So we'll times that by 6.67 times 10 to the negative 11. And when we do that, we finally get that the force of gravity is 8.34 times 10 to the negative 5th newtons. Okay? So there we go. There's our answer. Okay? So even with these huge objects, I mean 1,000 kilograms and 5,000 kilograms, only 2 meters apart, it's only 10 to the negative 5th newtons. Okay? That's like an 80 millionth of a newton. Okay, so not very large at all, even with these very massive objects. Okay, so you'll find that most of your answers are going to be pretty small unless you're dealing with very large objects like planets. Okay, but there you go. So it's not too bad. The main thing is just making sure you understand how to use your calculator to get the answers correctly. Be careful when you're putting in with scientific notation. Okay, and so I recommend you go back and review how we did scientific notation and plugging it into our calculators. I recommend using the double E notation that they do a lot on like the TI-84s. Okay, but make sure you know how to use your calculator. Okay, because that's going to be the biggest thing with these types of questions. Okay. All right, let's do one more. Just make sure we got this down. Let's use a real life example. Okay. So Mercury has a mass of 3.28 times 10 to the 23 kilograms, and the Sun has a mass of 1.99 times 10 to the 30 kilograms. If Mercury is 58 gigameters away from the Sun, how much force does the Sun put on Mercury? Okay. So when we're doing this one, we have to be careful with the units because we want to make sure everything's in SI. Okay, so there's our mass 1. I won't rewrite it this time, but mass 1's there, mass 2 is there. Okay, and then our distance is 58 gigameters. That's R. But let's be careful when we write this down because, again, we want it in meters. And if you recall, giga means billion or 10 to the 9th. So this is really 58 billion meters. Okay. So R is 58 billion meters. Or if we're writing that in scientific notation, we could say it's 58 times 10 to the 9th meters. But if we want to be really specific and really careful, let's put this in true scientific notation and move the decimal over 1. So now it will become 5.8 times 10 to the 10th meters. Okay. Now you don't necessarily have to do that. 58 times 10 to the 9th will give you the same answer. But when I do my answers, I want to make sure I'm truly in scientific notation so I don't mess anything up. Okay. All right. So now let's go through and do this problem. So we got F of G, or force of gravity, equals, again, I'm going to leave big G alone for a second. So big G times 5.8, or sorry, mass 1, which is 3.28 times 10 to the 23rd. All that times 1.99 times 10 to the 30. Okay. And all of that is over the radius squared. So 5.8 times 10 to the 10th squared. Okay. Don't forget that squared or it'll throw off your answer. Okay, so let's go through this on the calculator, and let's make sure we get the same answer. I recommend following along on your calculator to make sure you're doing it right, because this is where a lot of students get mixed up. Okay, so we're going to do 3.28 times 10 to the 23 times 1.99 times 10 to the 30th. Okay, and again, I kind of recommend that E notation for the TI-84s if you have one of those. Okay, all that is divided by 5.8 times 10 to the 10 squared. Okay, so if you write that all out and you put it in your calculator correctly, you should get that all this stuff right here is going to simplify down to 1.94 times 10 to the 32nd. Okay? So, again, double check on your calculator right now. Make sure you're doing it right. Make sure you're putting it in right. Okay? Until you get 1.94 times 10 to the 32nd. Okay? Now the last step is to times by g, which is 6.67 times 10 to the negative 11. So 6.67 times 10 to the negative 11. So when all is said and done, you should get that the force of gravity is 1.29 times 10 to the 22nd newtons. Okay? That's how strong the pull of gravity is between Mercury and the sun. Okay? So again, double check this right now. Make sure you're putting it in your calculator correctly. These problems aren't too hard. You just got to plug them in. But the main thing is making sure your calculator, you know how to use your calculator to get the answers correctly. Okay? But there we go. And now we can calculate the force of gravity between any two objects. Okay? Before we end, let me talk about units really quick. I've been kind of ignoring them and just saying, hey, look, it works out to be a Newton. Okay, but let's see why. Okay? So let's go back to this thing. So if you remember, these units are kind of weird. Meters cubed over kilograms second squared. And somehow this all ends up to be a Newton at the end. So let's see why this is the case. So if the force of gravity is G times M1 times M2 over R squared. Okay. Well, let's replace units. So M1, mass, is going to be a kilogram unit, right? So that's going to leave me with kilograms. Likewise, mass 2 will give me kilograms. And R squared will give me meters squared. Right? So that's going to leave us with a kilogram squared over a meter squared. And then G is going to leave us with these units right here. Okay. So that's going to give us meters cubed over kilograms second squared. Okay. So after we do that, notice what cancels out. Okay. This kilogram will cancel out with that kilogram. This meter squared will cancel out with 2 of these meters. And when we look at what's left, we get that that ends up with kilogram meter per second squared. And hey, what do you know? That's the exact same thing as a Newton. Okay. So even though these units look kind of weird, they do give us newtons in the end. Okay. So with these problems, since they're so long with all the scientific notation, I don't want you to worry about the units as much. Just make sure everything's in SI before you start the problem, and then you should be in newtons at the end. Okay. Alrighty, but that's it for today. Let me know if you have any questions, and thank you for watching.